Good morning, students. This is Dr. Louise Liu from Texas A&M University, Kingsville. So today we start your Chapter 5, Gases and the Kinetic Molecular Theory. We are going to cover three major topics. The first one is the overview of the physical states of matters. The second one related to the gas pressure and its measurement. Particularly, we are going to focusing on the pressure unit conversions. The third topic will be related to the ideal gas law and a theoretical model. So you can consider that's your fourth topic, the kinetic molecular theories. Regarding to the real gases, we are not going to discuss it in our class, but it's up to you to further study. First of all, let's discuss about the physical states of matters. Before, you already learned, generally speaking, there are three different states. One is called solid, second one called liquid, third one called gases. How do you distinguish gases from the liquid and solid? So you are going to use the properties of the gas. So you have four different properties of your gases. First one, your gas changes dramatically in terms of the volume, pressure, and temperature. And your gas flows very freely. The gases have very relatively low density. Gases can form a very uniform solution in any proportions. In other words, your gas molecules are freely miscible with each other. In terms of the gas volume changes, you also have two different points. If you change the pressure, the gas volumes is going to be significantly changes in an inverse order. Solid and liquid volume barely affect by the pressure. Your gas volumes change dramatically with the temperature change. If you increase the temperature, your gas will be expanding. So whenever you heat it, if you decrease the pressure, the temperature, your gas is going to be cooling. Gas going to be shrinks. So the volume changes in corresponding to the absolute temperature. Followed by, we are going to learn how you are going to measure the pressure. The pressure, in generic speaking, pressure equals to the force, external force divided by the areas. For your atmospheric pressure, you are going to measure by the force exerted by the atmospheric gas on the Earth's surface. Your atmospheric pressure decreases with the altitude. You can measure the pressure by using a barometer. Usually you use the mercury barometer to measure your gas pressure. So traditionally what we are doing, you have this evacuated flask and then you link to the two U-tubed shapes. So one U-tubed and second one. You place the mercury liquid metal into this U-tube. You adjust it to keep the both tube arms have the same amount or same height of the mercury. So in this first graph, your mercury level are equal because both arms of U-tube are evacuated. So this side is a close end. You also evacuate it. If both sides are evacuated, meaning you have no pressure, if you release this valve, you allow the pressure is going to be entered into your flask. What's going to happen? Your mercury from this side, because you have your gas, the gas is going to press the mercury down on your left hand side. Correspondingly, on your right hand side, the mercury level is going to be increasing. The difference between these two heights is related to your gas pressure. The difference in the levels from two arms of your U-tube, delta H, equals to the pressure of your gas, P gas. How do we describe it? commonly used units of the gases, including the following. The first one is called Pascal. That's your SI standard unit. The second one called kilopascal. The third one is the regular, what we are using, called standard atmosphere, ATM. This ATM is corresponding to the different units. They have the unit conversion. So if you have ATM, you want to convert it to Pascal. 1 ATM equals 1.01325 times 10 to the power 5 Pascal. 1 kilopascal equals to 1,000 Pascal. Millimeters of mercury, mmHg, is a very commonly used unit. So 1 ATM equals 760 millimeters of mercury. Tower is also very commonly used for the high vacuum. So 1 tower is the same as 1 millimeters of mercury. 1 ATM equals 760 towers. In US, we also use pounds per square inch. Also, you call it PSI. 1 ATM equals 14.7 PSI. There is another unit, bar. Usually the standard pressure refers to 1 bar. However, 1 ATM is approximately equals to 1 bar. 1 ATM equals 1.01325 bars. So there is only have 1.3% differentiation. These values, they are called normal atmospheric pressure at sea level at 0 degrees Celsius. So we are going to do a little conversion. You have a problem. Here there is a geochemist who heated up limestone, calcium carbonate, and then collected the carbon dioxide released in the evacuated flask. And then this flask, as we showed before, you attached to the closed-end parameter. What you measured at room temperature, your delta H, the differences between the mercury level, is found to be 291.4 millimeters of mercury. The question is, calculate the pressure of carbon dioxide in towers, in atmospheres, in kilopascals. Solution. You simply using this table based on the conversion factor, you can do the conversions. 291.4 millimeters of mercury, you convert 1 millimeters of mercury to tower. We already know tower and millimeters of mercury, they are the same as each other. Therefore, equals 291.4 tower. Second one, convert the tower to ATM. So you can see 291.4 towers, you convert this tower to ATM. From the above table, we know 1 ATM equivalent to 760 towers. Therefore, your ATM is 0.3834. You convert this ATM to kilopascal. From the above table, 1 ATM equivalent to 101.325 kilopascals. So you can do the conversion. Take home message. How do you convert this 291.4 millimeters of mercury into the PSI? That's the take home message. So followed by, so we are going to show you the ideal gas laws. Generally speaking, ideal gas laws can be expressed by the equation P times V equals nRT. In this ideal gas law, you can describe the physical behavior of gases in terms of the 4 variables. The first one, the pressure, P. The second one, the temperature, capital T. The third one, the volume, capital V. The fourth one, the amount of gases, usually refers to the moles, smaller m. The ideal gas is the gas that exhibits linear relationship among these four variables. In the real world, for your real gas, those four variables, they may not have this linear relationship. However, if the temperature and the pressure are moderate, so this linear relationship has been established. So no ideal gas actually exists, but most of the cases, simple gases behave nearly ideally at ordinary temperature and regular pressures. So this ideal gas constant R, capital R, also called the universal gas constant, is a numerical value, depends on the unit you are used. In our chapter 5, you are going to use ATM times liter per mole per Kelvin. This value was defined at 1 ATM, 22.4 liters of any molecules for 1 mole at 0 Celsius or 273.15 K. This value was calculated to be 0.08216 ATM liter per mole per Kelvin. Try to remember this number. R equals 0.08216, 8 to 16. And then we are going to further discussing your ideal gas laws. Your ideal gas law can be also changed its form by this case. If you use P1, V1, P2, V2, T1, T2 representing the different conditions for the same amount of moles of gas, the same moles, so you can simplify your ideal gas law to this kind of expression. P1 times V1 divided by T1 equals P2 times V2 divided by T2. And then we are going to study several special ideal gas laws. If you fix some conditions, we are going to summarize it for you in the following slide. So those ideal gas law again is described as PV equals nRT. Your ideal gases behaves ideally, especially at the STP state. STP stands for standard temperature, standard pressure. Standard temperature refers to the 273.15 K. Standard pressure more accurately refers to 1 bar. However, 1 atm is acceptable, or you can consider 760 Celsius. There is another value you should know. It's called the standard molar volume. This standard molar volume for any gases at a standard state equivalent to 22.4 liters. For the individual gases law, as specified cases of the ideal gas laws. For example, Paul's law. If you fix the number of moles and the absolute temperature, so your Paul's law tells you volume is inversely proportional to the pressure. Volume equals the constant divided by P, or P times V equals to a constant. The second law commonly used is called Charlie's law. Charlie's law tells you if you fix the moles and pressure, the volume is directly proportional to your absolute temperature. V equals the constant multiplied by T. The other law, if you fix the pressure and temperature, so this is called Avogadro's law. Avogadro's law tells you the volume is directly proportional to the number of moles. There has some law called Amante's law. Later on, we are going to show you. Let's practice Paul's law. Paul's law tells you the relationship between the volume and the gas of your, and the pressure of your gases. What we can summarize, at a constant temperature, the volume occupied by a fixed amount of gases is inversely proportional to the external pressure. You can simply use P times V equals to a constant. Make sure your temperature is fixed, your moles is also a constant value. In this case, if your P pressure increases, your volume decreases. If your P pressure decreases, your volume will increase, as we see in this graph. Your volume is inversely proportional to the pressure. And we are going to show you an example. So very briefly, so you are going to do this. You trap some gases in a J tube. This gas has a volume 24.8 centimeters squared at 1.12 atm. What you are going to do, you increase the pressure by adding more mercury. So you are increasing the pressure to the P2 2.64. So what I want to know, if you have your temperature at a constant value, what is the mu volume of the air trapped in the tube in liters? So what you measure is in milliliters, centimeter cubed in milliliters. What's your plan? The temperature and the amount in this case are fixed. So the temperature is a room temperature. And your amount of gases you may not know, but you know is trapped in J tube. So therefore the temperature and the moles are fixed. You are going to simply use the volume and pressure relationship. So you have your volume 1, I will write down volume 1, 24.8, volume 2, you don't know. Pressure 1, 1.12, pressure 2, 2.64. So you are going to convert your volume from centimeter cubed to liter. And then you simply apply those values into the equation P1, V1 equals to P2, V2. And then first one, solution. I may suggest write down your known values, and then the unknown values also write it down. You are going to use the equation, so you reorganize it. Figured out number 1, the volume conversion, so from 24.8 becomes 0.0248 liters. And then you are going to apply your Bowley's law. Your Bowley's law, P1, V1 equals to P2, V2. Your V2 equals V1 times P1 divided by P2. You simply replace your numbers into your equation. My calculation, my V2, 0.0105 liters. You can see your volume decreases with the pressure increase. That's how you apply Bowley's law. Charlie's law. Charlie's law tells you the relationship between the volume and the absolute temperature of your gases. Make it simple. At a constant pressure and a constant number of moles, the volume occupied by the gas is directly proportional to the absolute temperature, meaning your temperature must be in Kelvin. If your temperature is not in Kelvin, make sure you convert it to Kelvin. So what you can see, at fixed pressure and number of moles, you increase your volume, your temperature will increase. With the temperature increases, volume is going to be increased. On the other hand, if your absolute temperature decreases, your volume will decrease accordingly, or vice versa. Temperature decrease, volume decreases. Decrease in volume resulted in the decreases in temperature. Avogadro's law, as we already mentioned, if you consider the temperature which is fixed, pressure is also a constant value, your number of moles and the volume are directly proportional to each other. Your volume is directly proportional to the number of moles. You simply use the Avogadro's law to express it. So let's practice some other questions, such as we are going to apply the volume amount relationship to determine the amount of helium. So what you have, a scale model of a blimp raises whenever it's filled with helium to a total volume 50.0 decimeter cubed. When you enter the gas helium 1.10 into this blimp, you figured out the volume is 26.2 decimeter cubed, dm cubed. The question is, how many additional grams of helium must be added to make it rise? In this case, you assume the temperature is constant, the pressure is also constant, although with this altitude increases, so your temperature and pressure, they may change, but we assume essentially the same. What's your plan? Plan is, number one, you need to know the number of moles, N1, the number of moles, N2, and then you are going to apply Avogadro's law. And then you subtract 2 moles for N1 and N2 to determine the additional moles of helium, which you added into your blimp. And then you convert the volumes into the grams by multiplying the molar mass. So here is my suggestion. Number one, write it down your N1, which is 1.10, corresponding to 26.2. N2, you don't know, corresponding to V2. And then you apply the Avogadro's constant, V1 divided by N1 equals V2 divided by N2. Your N2 can be calculated. Your N2, my calculation is 1.10 moles multiplied by 55.0 decimeter cubed divided by 26.2 decimeter cubed. This volume you don't have to change to anything else. Just liters stay as liters, centimeter cubed stay as centimeter cubed, because they are cancelled out. Your total moles of your helium, which is 2.31 moles. The additional amount equals to the subtraction of 2.31 by 1.10. Subtract your two values. My calculation is 1.21. This is the additional moles of helium. You convert these moles into grams by multiplying by its atomic mass. My calculation is 4.84 grams for your helium. That's the additional amount of helium you need to add. And another very important variables we already mentioned is called the standard molar volume, which is 22.4 for any substances, regardless of the different types, helium, oxygen, nitrogen, hydrogens, whatever the gases. So the standard molar volume is 22.4. What do you mean by standard molar volume? Molar volume refers to per mole. Every gases you have 1 mole. The pressure is 180 m, as I mentioned. More accurately should be 1 bar, B-A-R. Your temperature, make sure is 0 Celsius or 273.15 K. The number of gases of any particles is the same as your Avogadro's constant. Your mass, you know the molar mass or atomic mass or molar mass, and the density, you can calculate it. So what I want to mention, the larger the molecule is, the heavier the molecule is, the bigger the density is. So usually what you found your gas is a mixture. The mixture such as you have your balloon. You are going to balloon up by the air will be nitrogen, oxygen, carbon dioxide, little helium, etc., etc. So that volume of 1 mole of the ideal gas is a very familiar object. So 1 gallon of milk, so basketball is equivalent to 1 mole of the gases. similar, so have some similarity, if have some familiar objects, as 3.8 gallons of milk. For your basketball, 7.5 liters. For your carbonated drinks, that will be 2 liters. That's essentially about the standard molar volume, 22.1. There's one more topic I want to show everybody. So today, the ideal gas density. Ideal gas density can be derived from your ideal gas law. You have your this PV equals nRT, your N equals mass grams divided by its molar mass. And this molar mass can be calculated. This molar mass can be calculated by the sum of atomic mass. Your grams, the grams related to the density. Your grams divided by density, divided by volume give you density, or vice versa. Gram divided by density give you volumes. Therefore, you derive your density from your ideal gas law. D, density equals to molar mass times pressure divided by RT. Let's try an example. You are going to calculate the ideal gas carbon dioxide density in two conditions. First one at the standard state, second condition at room temperature 180 M. What's your plan? You are going to calculate the molar mass of CO2, and then you simply use this equation as your guideline. D equals to the molarity, equals to the molar mass times by pressure divided by RT. For the first case, standard STP state, so which is 273 Kelvin, 180 M. So your molar mass for carbon dioxide calculated, my calculation is 44.01 grams, multiplied by pressure 180 M, divided by your ideal gas constant 0.08216 80 M liter per mole per K, multiplied by your temperature 273. Cross out the same quantity, my calculation is 1.96 grams per liter. The second condition, at 20 Celsius, 180 M. Similarly, you are going to calculate the molar mass of carbon dioxide. You also need to convert 20 Celsius into Kelvin, plus 273.15. And then you replace your molar mass, 44.01 grams per mole, into your equation, multiply by 180 M, divided by 0.08216, 80 M liter per mole per K, multiplied by 293. My calculation for the second condition, the density is 1.83. What you also see, your density is directly proportional to the molar mass. The bigger the molecule is, the higher the density is. Also, the density is directly proportional to the pressure. The higher the pressure is, the higher the pressure is, the higher the density is. The density is inversely proportional to the absolute temperature. With temperature increasing, your gas becomes lighter. That's all for today. Thank you so much for listening. Stay safe and stay healthy.